In this video, we'll explore a different way of acquiring data. We'll look particularly at scraping data from the internet using a package called rvest. We can't always rely on nice tabular data to come and land on our desk, whether that's nicely formatted or otherwise. Sometimes we're going to have to go out and gather data for ourselves. I'm not suggesting that you'll need to do this manually, but you will likely need to get data from the internet that's been made available either publicly or privately to you. This might be information from a web page that you gather for yourself, or data shared with you by a collaborator using an API. In this lecture, we'll focus on the web scraping element and then revisit APIs later. So before we can even hope to get data from a web page, we first need to understand what a web page is. Web pages are written in a similar way to LaTeX. The content and styling of web pages are handled separately and are coded using plain text files. In fact, websites go one step further than LaTeX does. The content and styling of websites are written in different files and in different languages. HTML, or hypertext markup language, is used to write the content of a web page, and then CSS, cascading style sheets, are used to control the appearance of that content when it's displayed to the user in a web browser. A basic HTML page with no styling at all applied to it might look something like this. It's just like an XML data file that we saw earlier. Just like an XML data file that we've met already, HTML has a hierarchical structure, and this structure is crafted using HTML elements. We'll come back to look at these in a bit more detail shortly, but first let's have a look at what this page looks like in a browser. When we load that HTML code in our web browser, this really basic HTML script would look something like this. Since HTML files contain only the content and structure of a web page, this looks pretty basic. Formatting that gets applied with a CSS file is what gives web pages their unique feel or brand identity. A really nice way of seeing this distinction is the CSS Zen Garden project, which is designed to highlight this difference by inviting lots of people to get as creative as they can, applying different style sheets to a single HTML document. Each element of a HTML document is made up of a start tag, some optional attributes, and then an end tag. We can see each of these in the first level header that's given on line 6. The opening tag is the h1 that's enclosed in angular brackets. These are just less than and greater than signs. Then an additional attribute is given within the opening tag. Here it's an ID being equal to the string first. Finally, the / followed by h1 enclosed in angular brackets is the closing tag for this element. Everything that we have between the opening and closing tag are the contents of that element. There's also some special elements that consist only of a single tag and optional attributes. An example of this might be the image tag that we see here. One thing to be aware of is that since greater than and less than are used for start and ending tags, you can't use them directly within a HTML document. Instead, you have to use something called escape characters. This sounds a bit fancy, but it's just an alternative way to write characters that serve some special purpose within a language. So if you wanted to write greater than, you'd instead write an ampersand GT semicolon. If you wanted to write less than, you'd instead write ampersand LT semicolon. And you might notice here that those escapes are using the special character for and, the ampersand. This means that if you want to include a literal ampersand on your web page somewhere, you're going to have to use an escape character too. And this one is informatively called ampersand amp semicolon. There's a really wide range of possible HTML tags and escapes that you might need to use. We'll cover the most common tags in this video, but you don't need to worry about the escapes too much, because the rvest package that we'll be using will automatically handle these for you. So in all, there are in excess of 100 different HTML elements. You definitely don't need to know all of these off the top of your head, and we're going to cover the most important ones of these now. The critical one that has to be in every single HTML document is the HTML element, and that has to enclose every HTML page. This HTML element then has two child elements within it in every HTML document. There's the head element, which contains metadata about the document. This is things like the page title that's shown in the browser tab, and the CSS style sheet that should be applied when displaying that page to the user. The body element then contains all of the content that you'd see when this page is generated within your browser. The next type of element are block elements, and these are used to give structure to the page. These elements are things like headings, subheadings, and so on, going from H1 headers all the way down to H6 headers. This category of block elements also contains things like paragraphs, ordered lists, and unordered lists. Finally, inline tags are used for things like making text bold, italic, or adding hyperlinks when formatting text inside some sort of block element. When you come across a tag that you've never seen before, you can usually find out what it does pretty easily with just a little bit of Googling. And a good resource to use here are the MDN web documents, which are produced by Mozilla, the company that makes the Firefox web browser. An alternative resource are the W3 Schools websites, which are a great resource for web development and coding more generally, but particularly in this instance for learning HTML. We've already seen one example of a header with an additional attribute. More generally, all tags can have named attributes, and these attributes are contained within the opening tag and look something like the code that's shown here. Two of the most important attributes are ID and class. These attributes are used in conjunction with the CSS file to control the visual appearance of the page. These are often very useful attributes to identify the elements that you're interested in when scraping data from a web page. So moving now from the HTML to the CSS element of a website, the cascading style sheet is used to describe how your HTML content will be displayed. In order to know how each element of your HTML document should be formatted, CSS has its own system for selecting elements of that web page, and these are called CSS selectors. Selectors define patterns locating the HTML elements that a particular style should be applied to. A really nice side effect of this is that they can sometimes be incredibly useful for scraping, because they provide a concise way of describing which elements you want to extract. CSS selectors can work on the level of an element type, a class, or a tag, and these can be used in nested or cascading ways. So let's see some examples. The P selector will select all paragraph elements. The title selector will select all elements with the class title. And we can combine these, so the P.special selector will collect all paragraph elements with the class special. Finally, the title selector will select the element with the ID attribute equal to the string title. When you want to use a single element, this sort of ID attribute can be really useful, because one of the features of an ID attribute is that it must be unique within an entire HTML document. Unfortunately, though, this is only going to be helpful if the developer initially thought that that element was so important that they should add an ID attribute to it in the first place. If you want to learn more about CSS selectors, I recommend starting with the fun CSS dinner tutorial, which is a really good way to build up a base knowledge of CSS. And then you can go on to use documents like the W3 Schools resources as a reference text when you're exploring more web pages in the wild. So to know which data you want to scrape from a web page, you first have to identify the tag and attribute combinations that you're interested in gathering. To find your elements of interest, you've got three options, and I'm listing these here in order from hardest to easiest, but also from most to least robust. Your first option is to right-click on the web page and then select the option that is similar to Inspect Page Source. The keyboard shortcut to this is usually F12, and it will show you the entire HTML source of the web page that you're currently viewing in your web browser. A more specific way of doing this is to right-click on the element that you're interested in and click on Inspect or Inspect Object, depending on which browser you're working in. This again will open the full source of the web page, but it'll open it at that particular element. What can be tricky here is making sure you right-click in exactly the correct place for the exact part of the web page that you want to scrape. A useful tool in making sure you get that right part selected is the rvest selector gadget. But one thing to be aware of here is that it's using some fairly simple heuristics, so even though it's usually very useful, it's also fallible. What I'd recommend here to get used to these different elements and where they might appear on a website is to inspect the source of some familiar websites that can be used to get your head around these concepts. What you should be aware of, though, is that some sophisticated websites can be quite intimidating to look at the source code of. A good place to start is with simpler static websites, things like personal websites, rather than the dynamic web pages of online retailers or social media platforms. So now that we've got an idea of what a web page looks like under the skin, let's have a look at how we can read some HTML using the rvest package. With the rvest package, reading a HTML page can be as simple as loading in tabular data into R. We can do this with one function, read_HTML, which, like read_CSV, is just going to take a single argument, but rather than being the file path to our CSV, it's going to be the web address that we're trying to scrape from. We can see here that the class of the resultant object is going to be an XML document, and this is a type of object from the low-level package called XML2. And this is a package not designed for direct interactions, but provides functionality to read XML files into R. In the bottom code block, we can see that this object is split into several components. First is some metadata on the type of document that we've scraped, followed by the head of that document, and then finally the body of that HTML document. From here, we've got several possible approaches to extracting information from this XML document, depending on exactly what we're interested in. To begin, let's suppose we're interested in extracting some HTML elements. In the rvest package, you can extract a single element using the HTML element function, or all matching elements with the HTML elements function. Both functions here take a document object and one or more CSS selectors as inputs. In the top code block are examples of extracting the first level header, all second level headers, and all paragraph elements of the web page. You can also combine and nest these selectors to make a more specific request. So, for example, you might want to extract all links that are within paragraphs and all second level headers. This is demonstrated in the second code block, where the space functions in the same way as an AND connection between the element types, and a comma functions like an OR connection between these element types. So now that we've got the elements that we care about extracted from the complete document, how do we get the data we need out of those elements? We usually get the data either from the contents of the HTML element or else from one of its attributes. If you're really lucky, the data that you need will already be formatted for you as an HTML table or list, so we'll take each of these cases in sequence and see how we'd extract that information. The functions HTML_text and HTML_text2 from the rvest package can both be used to extract the plain text contents of an HTML element. The difference between these two functions is how they handle whitespace. In an HTML document, whitespace and line breaks have very little influence over how the code is interpreted by the computer and how the web page is displayed to the final user. This is quite similar behavior to R, but might be quite alien to you if you're used to working in Python. The first function, HTML_text, will extract the text as it is in the raw HTML, keeping all spaces and line breaks as they are. Conversely, HTML_text2 will do its best to extract the text in a way that gives you something out that's similar to what you would have seen in the web browser itself. This is usually what you want to have. As well as the contents, attributes of tags are also used to record information, which you might be interested in collecting. For example, the destination of links are stored in the href attribute, and the path to the source files for images are stored in the src attribute. To consider a concrete example of this, think about trying to extract the Twitter link from an icon that is within the page footer. This can be really quite tricky to locate in the full HTML source, so I used the selector gadget here to help me find the correct combination of elements to select only that part that I was really interested in. To then extract the href attribute from this scraped element, we use the rvest function html_attr. This is a contraction of the word attribute. One thing to note here is that the rvest function will always return a character string or a list of character strings. If you're extracting an attribute that describes a quantity, so this is things like the width of an image, you'll need to convert that from a string into your required data type. So you might have to use as integer, convert your image width measured in pixels into an integer that R can work with. So moving on now to that really nice case, let's consider the ideal scenario where the information you want is already formatted in a nice HTML table. A table in HTML is composed in a similar nested manner to LaTeX tables. There's 4 main elements to know when trying to make up a HTML table. First, there's the table tag, and this encloses the entire table environment. There's then one table row tag, which encloses each row of the table, and this stands true also for the header row, as well as rows containing the data. And finally, there's the table data tag, which encloses each entry in the body of the table. Let's see this in practice now. So here's our simple example dataset that we've seen before, formatted as an HTML table. There's a name column containing the letters A, B, and C, and then there's a number column containing the numbers 1, 2, and 3. We'll save this as a minimal HTML object called HTML2 to work with in R. So because tables are such a common way to store data, rvest includes a useful function called HTML_function that converts a HTML table directly into a tibble. And that's exactly what we've used in this example. We can apply this exact same workflow to our scraped website data that we had before and easily extract the table on teaching activities. We'll first extract the HTML table element using HTML_element, and then we format this as a tibble using HTML_table. So when you're scraping data from a web page, your end goal is typically going to be to construct a data frame or a tibble of that data. If you're following the ideology of tidy data, you'll want each row within that data frame or tibble to correspond to some repeated measurement unit on the HTML page. If this is the case, then you should first use HTML elements to select the elements that contain each observation unit, and then use HTML element in the singular to extract those variables from each observation. If you take this approach, then it'll guarantee that you'll always get the same number of values for each variable. This is because HTML element in the singular always returns the same number of outputs as inputs. This is really vital when you have missing data, when not every observation unit has a value for every variable of interest. We'll see this more explicitly with an example now. So the example we'll consider is an extract of text about the Star Wars dataset. This extract gives an unordered list where each list item corresponds to one observational unit. That is, one character from the Star Wars universe. The name of the character is given in bold, The character species is specified in italics, and then the weight of the character is denoted by the weight class. However, what we should notice here is that some characters only have a subset of those variables defined. So, for example, Yoda has no species entry. If we try and extract each element directly, then our vector of variable values are going to be of different lengths. Since we don't know exactly where those missing values should be fitted back in within those vectors, we can't replace them and make a tibble from this data. We can't combine vectors of different lengths. What we should do instead is start by extracting all of the list item elements using HTML_elements, plural. And then once we've done that, we can use HTML_element, singular, to extract each variable for all of the characters. If we do this, then our variable values will be padded with NAs, and that means that we can collate them into a single tibble. So with that, let's wrap up this video. What have we learned? We've learned about the way that web pages are structured and how this structure can help us locate parts of the web page that we'd like to extract. We then covered how functions from the rvest package can be used to easily extract this information from a website. And finally, we considered how to convert these extracted HTML elements into R objects that are amenable to further analysis. What this means is that in this video, we've covered all you need to get started scraping your own data from the internet. Thank you very much for your attention, and I'll see you in the next video.